Okay, so last time we were in this lab 2, and we looked at the first 2 exercises. Now there's a third exercise to go over, so I'm going to do that today. So generating random numbers. So we'll use what's called a loop, and we'll generate 100 random integers in this loop. So generating a random integer and displaying it is an operation that we can do. But if we want to do it 100 times, then we need some way of repeating that operation, something that's convenient. We don't want to just repeat. We don't want to we don't want to copy and paste those operations 100 times in our code. We want a mechanism that sort of allows us to repeat the operations, and that's what's called a loop. All right. So let's start with, and I'm going to cover the interaction with the Git repository a little bit today. So I set up a sample account that I can use to show you what you need to do to commit your work to your remote repositories, which you've already been doing, but I think it helps to see it because it does take some time for the steps to sink in. Now I don't have the repository right now, so I need to clone it. So I'll run my clone command. So my username is Sam. I'm cloning the repository. I use the ls command to display the contents of my current directory. By the way, what is my current directory? Print working directory. I'm there. So I'm working on my local system. This is a Mac, so I'm running OS 10. And inside this folder, this temp folder, I have another folder, 201. That is my cloned repository. So now that I'm in 201, I see when I print working directory, I'm down a level. Let's take a look. In there's a README file. I used a cat command. Just a cat command lets me dump the contents of a file to the screen. And I need to run these 2 commands. And I think most of you have done this already, but some of you haven't. So I'm just going to repeat that. So that's that setting, and you only need to do this once. And there's my email. And we're working on lab 3, so I'm going to create, lab 2. So I'll create a directory called lab 2. So mkdir. And there is the lab 2 folder, and I'll cd into that. There's nothing in there. I just created it. It's empty. Now, I'm going to use this screen program. It gives me access to what are called virtual screens, so I can have several virtual screens open and toggle between them. No, that's optional. You don't need to know that, but it's very handy, by the way. All right, so print working directory, this is where we're located. Let's create ex3.cpp. That's the name of the file, the source code file, that you need to create for the third exercise of lab 2. And these are the instructions. And before I even do this, what I want to do is compile a hello program first. Make sure that I've got things set up. I want the container. I want to make sure that I've got a basic source code file that's ready to be modified. So I'm going to get a copy of the hello program that we did in Lab 1. There it is. So this program simply displays the word hello. Oops. I'm in VI, by the way. I need to go into insert mode. I press I for that. There it is. Now I press escape to leave insert mode. :W to write. I do Control C to create a new virtual window for those who want to use screen. Now I see that I just, in VI there, I created the file ex3.cpp. Let's compile that. Now if I do ls again, I see that a.out was generated. That's the executable file that was generated from the source code. Let's run that. So it says hello. That's what we want. So we're we're at the starting point. All right, let's go back and look at the problem definition for problem 3 in Lab 2. Write a program that generates a list of 100 random integers. The C++ standard library contains a pseudo-random number generator that you can use to solve this problem. And we need to include this header in order to have access to that pseudo-random number generator. So let's add that. If you want to be very incremental in your development, you could just verify that that header file exists by running the compiler. Oh, now I know, oh, what I just pasted in there is good. Look at how incremental that is. I verified that the header file is good and I pasted it in correctly. And I do recommend that kind of incremental development. Let me show you what would happen if we got a bad header file. And just to make sure it's bad, I'll just put a lot of stuff. I know that that's a bad one, right? What would that look like? Fatal error, file not found. Okay, so let's get back to a good state. All right, now we're back to a good state. Once again, this is incremental development where as I'm learning new things, I verify each thing and make sure that each step that I take is good. All right, so now this lets us use a function called rand. And the rand function returns the same sequence of values for a given seed. So it's a pseudo-random number generator. It's not a true source of randomness. It looks random. That's why we say pseudo. So it's falsely random, but it looks random. If we call rand over and over again, we'll always get the same sequence of random numbers every time we run the program. So if we want a different sequence, we have to pass in a different seed value. And I'm going to just sort of put some of this in context that might be interesting to you. Let's see. First, let's see if that works. It compiles. All right. I'm sure that it runs as well. So seeding random numbers. Now we're just gonna take a little diversion here. Something that that might be of interest to some of you. Yesterday, I received a Raspberry Pi in the mail. Does anybody have one of these? Let me find the wiki. There it is. So that's a Raspberry Pi right there. It's a computer, and it's sold. It was designed and it's provided through a nonprofit organization. I think it was built in Cambridge or something like that. And here it is, a developer of the Raspberry Pi Foundation. So it's increasingly being used in educational context to to learn about computing. And it's cheap. Look, it says here US dollars, $25. I mean, I paid $35, so I don't know where they got the price 25, but it's pretty cheap. So for $25 you get, and this is a complete, in a sense, it's a complete computer. I mean, it doesn't have a console, doesn't have a keyboard, it doesn't have a disk drive, but it works on flash memory. And the device that I got has 8 gigabytes of flash memory on it. And when I ordered mine through Amazon, but you could buy it through other outlets as well. It came with an operating system pre-installed called Raspbian, and it's a variant of Linux, or it's a distribution of Linux, I should say. So it came pre-installed. So all I needed to do was plug the flash memory card into the device and then plug it in and turn it on. There's no on-off switch, by the way. You just plug it in and it stays on, and you unplug it to turn it off. But it is Linux. And so last night I got this, and I've been tinkering with it, and I want to show you a little bit about that. I'm going to tie this in, by the way, I'm going to tie it into our assignment here just to try to make it a little more meaningful to you. So, I set up this script here. Now, I'm working in a Linux-like and a Unix interface here, so I'm at the command line. And a lot of the way I interact with the Raspberry Pi will be similar to how I interact with the OS X operating system. So there's a script here, bash rc. This thing runs whenever I create a terminal window. And look here, there's an alias that I defined called pi, and it's when I issue that at the command line, it's replaced by this command, ssh csusbdt.noipbiz. So that's I'm using this noip service to sort of track the IP address of my home internet. Does anybody use noip? So if I run this, I secure shell. I haven't tried this yet, by the way. I just got this last night, and I spent the evening tinkering with this. But I'm logged into the Raspberry Pi that's in my house. And in my house, I have this thing here, and look at this. This part of it right there, which you can't see, that's where you plug in the network cable. So I have it sitting next to my wireless router, and it's cabled over to the wireless router. So it has a wired connection to my router. And I'm connecting to it now. So I'm logged into my little Raspberry Pi, my $35 computer. And as my first experiment, I set up a Minecraft server. Anyone play Minecraft in here? Yeah, a lot of people, right? So I got it to run. I mean, this $35 computer, I got Minecraft running. I'm pretty happy with the performance, actually. And I'm using Screen. Look what happened. What I did is I created a detached screen session. And I'm going to resume that detached session with Screen -R. And I see that I'm still running. Look at this. That was this morning. And there's configuration files. I'm not running the server that is provided through the Minecraft company, or whatever they're called. They're not the company that makes Minecraft. I'm using something called Spigot. And I did a lot of experiments. I tried 3 different sort of versions of the Minecraft server till I got one that gave me good performance, and I could configure it. And so they have all these different configuration things in here. And let's look at one of the configuration files here, server.properties. And look at this here. That's level seed. This level seed is not set here, but you can set a seed value. And the whole of the world is generated. So Minecraft is a 3D virtual environment where the environment is generated randomly. So you get random worlds, and it uses a pseudo random number generator to decide where to put a mountain, where to put a tree, all that. But it's all based on a seed value. So if you modify the seed value, you're going to get a different world. But I think, I'm not sure, I didn't verify this. If you use the same seed value, when you create a new world of Minecraft, you get exactly the same initial world.
Yeah.
You do, right? There you go. So I'm tying it into the class here, and that's what this does right there. We're seeding our random number generator. That's like the Minecraft seed value that you play with to build out the Minecraft world. So actually, if you don't mind, I want to just try it. I want to see what the performance looks like if I actually run that thing. So I'm going to go ahead and start that so people know what we're talking about here. And I haven't tried this yet, so this is my first time. There it is. Oh, it's working. Incredible. Look at that. And look at that. Here's the problem, is that if I try to interact with the world, like say if I want to cut down this tree, what the heck? It was a creeper. Oh my gosh. Look at that. I survived. That used to be death, right? With one explosion. I think they weakened that. Here's the problem. See that chunk I was able to get. Now this one here, I didn't get this one, right? So now it's working fine. There's a little bit of delay, but it seems to be working okay. Anyway, so that's it. This is running on that $35 Raspberry Pi, so it's quite fantastic. I mean, I'm shocked that I could actually do this. But it's all, this is one of the things you can do, I guess I'm trying to show is, one of the things I'm trying to demonstrate anyway is, when you master the Linux interface, you can do fun things like this. You can basically set up web-based services, internet-based services like game servers and so on. And there's tons of work to do out there in industry doing these sort of things. So let me detach that session. I want to keep I invited some people to play on the server already, so I'm just going to leave that running in my house. There it is. There's the random number seed. And this is how you generate a random number. You call the rand function. Yeah, let's get rid of this. I'll just put a new line in there. So that's the random number. Now, every time I run that, I get the same, well, it's not really random, it's a pseudo number. So if I change this number here, I'll get a different value. But I get the same different value over and over again. Now what we want is when we run the program, just like generating a world of Minecraft, we want a different sequence of random numbers each time we run the program. So one way to do it is to, say, take a time value here and use that as our seed. So this number here is the number of seconds since January 1st, 1970. Number of seconds since January 1st, 1970. Let's use that as our seed value. Do I need a header file for that? I don't think so. All right, now, look here. Now we're we're calling a function times 0, and that function returns the number of seconds since 1970, and we pass that into SRAM. So now each time we run the program, we're going to get a different seed. Let's verify that. So let's compile again and run. All right, let's run again. Ah, it's not working. What did I do wrong?
They're different numbers.
What's that?
Yeah, they're different. They start the same.
Oh, it's different, isn't it? Just starts the same. Oh. Why is it starting the same? But it is different. Oh, okay, it is different. Okay. But it's not a lot different, is it? But let's, what we want to do is do it this 100 times. So let's put it in what's called a loop. Repeat the following 100 times. I should have made it 1,000, because you can just do this, right? 100 times. But there's no need for that. What we'll do is put it in a loop. So I'll show you first the while loop. Maybe I'll show you the while loop. What did I do here? Did I ask for anything? No. So it's while some condition do some statements. And so that's essentially the loop right there. While some condition is true, do the statements, do the substatements within the while, within this block that's part of the while loop. And so we need to create a condition that is true 100 times in a row and then becomes false. And so let's have a counter. So while a counter is, say, less than 100, while the counter is less than 100, let's initialize that counter. Let's set it to 0. Well, let's do it like this. And I'm going to change this around a lot. Well, we'll start to count at 1. And this is not going to stay this way. So I'm going to put it in a form which is more conventional. But this is a form that's more related to how people normally count. Normally, people start at 1, and then when they get to the number they're counting to, well, they got there, and they do what they need to do at the end, but in the next number will exceed it, and then it stops. So we need to, every time we run the body of the loop, we need to increment the counter. So these statements, and notice how I'm indenting. And it's not required by the compiler, but it's required by your instructor. And it's required by your future employer. Because it's hard to read the code unless you show inclusion with indentation. So these statements, these are 2 statements, and they are included as substatements within this larger while loop statement. So once again, when execution reaches this point, let's go through it sort of in a sequential manner now. Well, we call srand. We declare count, initialize it to 1, and then we execute the while loop. And the while loop is complicated. What it does first is it evaluates the loop condition. It's called the loop condition. I've highlighted the condition. The condition is count is less than or equal to 100. Well, that will be true the first time we enter the loop because we initialize count to 1. So if that's true, then we will execute the body of the loop or the substatements. And so the first thing we do is we generate a random number, that's this expression, and we send it to the output stream. We pass it through, we use the output operator and to send this integer value that we generate to the output stream. After we do that, we'll increment our count variable by 1. So we started at 1, now it's 2. Now, this is the last of the substatements. So the next thing that happens is that the system reevaluates the loop condition. So it's going to keep reevaluating the loop condition. Each time it's true, it will execute the loop. As soon as the loop condition becomes false, the loop statement has finished. And then we move on to the next statement, which is to do this. Remember, this is a statement. This is one statement. This is the next statement that follows that statement. At the top level, there are 4 statements in this program. As the call to srand is the first statement. The declaration and initialization of count is the second statement. The while loop is the third statement. Oh, can't believe that worked. And this last out, where we print the new line character, that is the fourth statement. Most of the statements are very simple, but the while loop is called a compound statement. It has substatements in it. We've already gone over how that works. So I'm repeating myself because I want you to think in these terms. I want you to see and recognize a statement and understand it as a statement, and that there are substatements in there. I want you to see the loop condition and understand when the loop condition is evaluated and what happens when it's evaluated true versus false. All right, there we go. Let's compile that. We run it. There's 100 random numbers, but we didn't output it very nicely. So let's do that. Let's put a space in there. And notice we're getting different numbers because like the last digit here is 3. Here the last digit is 1. So we're getting a different sequence of random numbers. The numbers are pretty big, but nevertheless they're there. Maybe what we'll do here is put in a new line character. There it is. 87748. Oh, and there's a different number. 1145, like that. Now, if we don't want the numbers to just display on the screen, we want to change the standard output stream. We want, instead of having it attached to the display, which is the default, we want to attach it to a file. And we'll call the file numbers. I'll give it a txt extension because that's a conventional extension to indicate that the data inside the file is pure character data. Notice that nothing got displayed on the console because we redirected standard output to the file, numbers.txt. You'll see that the file has been created. And we can look at that file, and there it is. And that's the command here. Now we need to submit this file into the source code repository. So we need to add the source code file to the staging area. Then we want to add the numbers file to the staging area. Then we will commit from the staging area to the repository, the local repository. That's where we take the snapshot. This is where we gather together the objects that we want to take a picture of, in a sense. And then here we take a snapshot of everything and have it stored locally in the local repository. Remember, the local repository, I'm going to use -A here to show the hidden files. The local repository is inside this folder, .git. You don't normally see it. So the commit command stores the changes, the new version of everything, in the local repository. But I can't access your local repository. I need to see your work pushed into the remote repository because I will pull from there. Or Jaron Willis, a TA, will pull from there. So let's go ahead and do that. And I can do it at this level or I can do it down a level. I can do it at this level here and do git add numbers.txt. See? Or I can be up a level and do git add lab _2 / ex3.cpp. So I'm giving a relative path to the file that I want to add to the staging area. And this is an optional command. You don't need this, but I'll show it to those who are interested. So if I do git status, it shows me what's ready to be committed. Changes to be committed. 2 new files have been created. Untracked files. These are files in the 201 folder that have not been staged and will not be added to the repository. Now, see that this file here, does everyone understand where that's coming from? What happened there? Look at the file starts with a dot, so it's hidden. So if I do ls lab 2, I don't see it. But if I do ls -a to display the hidden folders and files, then I see it. Where is that coming from? And by the way, there's dot and dot is also revealed there. Those are symbolic names for the folder and its parent. But what is this file coming from? Anybody know? So VI created that. That's the editor. Watch. If I exit VI and then I display the contents of the folder again, now .ex3.cpp swap is not there. So that's a backup file, temporary backup file. If I lose my internet connection or something goes wrong, I can restore. If I haven't saved my changes, then I can retrieve them, hopefully, from the backup file. And different editors use different conventions. This is the convention used by VI on my system. In the lab, for those students using gedit, you'll see a different name. I think there's a tilde at the end of the file extension. That's the backup file created by gedit. Now we don't want this in the repository. We also don't want a.out in the repository. So one thing you can do, and once again this is optional, but I'm going to show it anyway, is to create a file called gitignore, .gitignore, so it's a hidden file. And I'm going to list in there patterns that indicate the files that should be omitted, which will be omitted from listings by the git status command and other tools. So a.out is one, and another one is any file that ends with swp. That was the file, right? What's in here? I'm going to in VI again. See that? And if I look at the file contents, there it is. It got created again. So I'm in when I open VI, open that file in VI immediately creates the backup file. Now if I run git status, it shows that I only have these 2 files that are scheduled to be committed. It no longer displays that SWP file doesn't display the a.out either. But it shows .gitignore as a file that has been created but is now untracked. And so what I want to do actually is I want to put that in the repository. So I'm going to add that. Now when I run git status, I see that, I have 3 new files to go into the repository. These are staged. Now I'll use git commit with -m, that's a message, and I'll just say exercise 3 of lab 2. So that's not that important in our class, but messages are helpful. This is attached to the commit, so when you look at a long list of commits, you're going to get an idea about what happened when. So now if I run git status, it says I'm on the master branch. We will only work in the master branch, by the way. And it says we're ahead of origin master by 1 commit. Origin master is the name of the remote. Origin is where we cloned from. And master is the name of the branch. Once again, so we work, on branches. We commit branches. But we're only using one branch. We're going to keep it simple, called master. So there's nothing to commit, but there's something to push. So let's go ahead and do that. I'm going to do git push. You do git push origin master. That's the full command, but that's the default. So I'm just going to do git push. That's easier. And there's some delay on our network, so you got to be patient with that. I can see that this is a success, but you should read this to look for errors. But there's no indication of an error there. Now I'm inside this folder temp. Here's the 201 folder. Oh, I'm opening the editor here, by the way. I'll take that, get rid of that. And I can remove this 201 folder. It's a directory. I can't just remove a directory. I need to, RMDIR is remove directory. But it's not empty. For safety, it won't let me delete non-empty folders. Now I'm going to show you a dangerous command. Very, very dangerous. Recursive force -RF. So unless you really know what you're doing and you're very careful, don't use this. I'm going to force the deletion of that folder and all of its subfolders. And once again, there's no undo here. There's no trash can I can pull that out of. That's done. So if I did this on my home folder, I'd have to spend some hours rebuilding lost stuff. Yeah.
Isn't that where a branch would be useful? Like if you accidentally delete your master branch?
Well, no, I didn't act. I mean, it's just where the repository is useful, the remote repository, because I've deleted my work from the local system. But I just pull it off but I saved everything into the remote repository, so I can pull it, I can clone it again. It's gonna go way back here. Can I get to it? No, can't get to it. Git clone, I'm Sam at web2.is. So I'm cloning again from the remote repository. There we have our work. I use -A. I see, I've got the .git folder and the .gitignore folder that we added. Is that okay? The branch is used to do other things, branching. So we're done with lab 2. Any questions about lab 2? Yeah.
What would be the difference between doing a for loop and while loop?
Oh, yeah, thank you. We're not done with lab 2. Let's redo this, because actually the for loop is a more appropriate loop. And let me talk about that, and we'll rewrite this as a for loop. I'll use a multi-line comment. This is called a multi-line comment. I start the comment here, and I end the comment section there. Everything in between there will be ignored by the compiler. But we commented that out. Normally, here we have a loop that runs exactly 100 times. So typically, a programmer would use a for loop for that. The for loop looks like this. We define the loop like this. Oops. It's more compact. That's the same thing written as a for loop. And the for loop has this following syntax. It has this sort of control instructions, control section. And then it has the body of the loop, just like the while loop has a body of loop. You'll repeat. You can have many statements in there that repeat. But we have just one statement. And it's this control section in here that you need to understand. It has 3 parts. It has the initialization section. It has the loop condition. And it has the end of loop operation. Initialization, that means this code here, and the sections are separated by semicolons. The initialization section runs once before anything else in the loop runs. Here's the initialization we did for the while loop. So that's placed inside these parentheses in a for loop. And then the second section is the loop condition. You can see it's exactly the same loop condition. And sorry about that. It's not ++ I, it's ++ count. And at the end of the loop, after we've executed the body of the loop, then we increment the count there. We run this command. All right, let's test that. Where am I? Oh. What's going on? Oh, I messed something up. You know, I deleted the folder when I was in screen, and let me fix that. Looks okay. Oops. There it is. Okay. So we generated a.out. We'll run that. There it is. That works. Now, normally you won't see it like this. You know, count is a long word. Normally, you know, I is a variable that you'll see as a loop counter. That's more common. Not only that, but you wouldn't start at 1 and go up to and include 100. You would normally see it like this. You would start counting at 0, and the loop condition is that I is strictly less than 100. Because actually, internally, this is how, at the hardware level, counting is done. Counting starts at 0. And when you look at assembly language and low-level code, counting always starts at 0. It's a human thing to start counting at 1. Machines, they like to count. They like to start at 0. And so this sort of convention here to write the loop in this way, where you start counting from 0, and that you're less than your target number, that's a convention that comes from sort of working at the lower levels. But you know, these are all equivalent. We could do it like this. If I start at 0 and hit 99 and include 99, that's 100 steps. But once again, that's not common. This is common. So you might as well get used to reading this. That's what I'll be using in this class, and that's what you would normally see in other people's code. Just like that, the while loop would be the same thing. You know, this would normally start at 0 here, and that would be out. You know, if you want to use the variable count for clarity, that's great. You can use that. Maybe it's more expressive for you. But sometimes I, in these loops, I is usually an index into an array. And so I represents the index into an array. So that's why the letter I is sort of convenient for that reason. And we'll check that. That looks good. Any other questions about lab 2? Okay. All right, let's go to lab. Let's look at the assignment. So this is due. I recommend getting started on this, finish it now. And I want to show you how you would do this. So this is assignment 1. I don't think I mentioned anything. I didn't give instructions on that, but this is what I want you to do. Make a directory called, assignment 1, A1. And let's create our answers. Okay, answers.txt. And we'll look at the first question, which is, when this code runs, what does it output to the console? And so give your answer here. Maybe it prints, 100. And then exercise 2 is another answer. And when you're done, just add it to your repository and commit it and push it. That's it. That's what you do at the end, or at intermediate steps. That's fine. Now, for the labs, I don't mind showing you, all the steps and giving you the code, but I don't want to just give you the answers to the assignments. That's something you need to work out on your own. But what I will do is go through some practice problems that are just like the assignments that that appeared on quizzes in the past. Here's an example. Let's look at this. So this is a problem where you need to understand a chunk of code. So here it is, figure 1, this is figure 1. When this runs, when the code of figure 1 runs, what does it output to the console? So what does this output to the console? So let's read through it. Well, we initialize the variable I, we set it to 6. And then we have this loop. So while this condition is true, let's execute the body of the loop. And you see, actually my indentation is off here. I was going to fix that the other day and I forgot to do it. So this is, these two lines should line up, but they don't. This is off by 1 space. And when you submit your code, you need to have your indentation to be consistent and logical. All right, so we print something, and then we modify I. We use the assignment operator to modify I here. And then we use I in the loop condition to decide whether we're going to continue with the loop or not. So let's think through this. We did this one already, didn't we? Did we do this one? I think we did this one. So let's cheat. And maybe that's not a good thing to do, but the answer is 0, 30. So your answer is 0, should look like this, 0, 30. That's what it prints. All right, let's do the second problem. Suppose that t is an integer variable. Write code that prints cold when t is less than or equal to 50 and hot when t is greater than 50. Now, I'm not asking for a complete program. You don't need to compile this, test it, run it, okay? I'm asking for just a piece of code that does this. So suppose that t is an integer variable. So in a real program, you would have to declare t. You would have to do int t, equals 3 or whatever. But here you don't, because I'm saying suppose it exists. Suppose you have an integer variable called t. Write code that prints cold when t is less than or equal to 50. So if t is less than or equal to 50, then print cold. Sorry, cout. That's good enough. And print hot when t is greater than 50. Well, that's the opposite. So we could do it like this. And I'll spread it out. I'll use the spacious styling. That's it. That's what I'm looking for there. And let's suppose we do the rest of the problems, and then we have some document in our repository, and we add it. Now see, we're not adding the file, we're actually adding the changes to the file, to the staging area. That's what the add means there. The file is already in the repository, but the changes have not been added. And then we'll commit. And then we push. Other answers are acceptable here. If you had done this, that would be okay. Oops, this is wrong, right? Cout. On an exam, I wouldn't take offered at, by the way, because I'm looking for you to understand the logic, how to take this problem statement and express it using at least pseudocode. It doesn't have to be exact C++ code. But on the labs, you need to have exact C++ code that compiles and runs correctly. All right. What about this one? So these are problems. You'll be faced with these kind of problems on the quiz that's coming up. How do you figure this out? Let's do this one. When this code runs, what does it print? Well, it only prints in one place here. See that? Right at the end. And is not printing in the loop. So how much is it going to print? A lot or a little? It's a little. It's going to print one number, n, whatever n is. All we have to do is figure out what is n when the loop finishes. Well, there's more than n to think about because there's also k. K is declared, it's set to 2, 2, 2. N is declared and set to -4. The loop condition, then there's I, that's a third variable, which is initialized to 0 when we enter the loop. The loop condition depends on I and k. The loop runs if I is less than k, strictly less than k, which it starts out being. I starts out as 0, k starts out as 2, 2, 2. Actually, k is always 2, 2, 2. So we can mentally remove k from the problem and just replace k here with 2, 2, 2 because there's no code that modifies k. So the loop is I less than 2, 2, 2. That's the loop condition. And the end of loop operation is to increment I. And what do we do inside the body of the loop? We modify n. We add 2 to n. See, we take, this is assignment, so we're modifying n. We take what's in n now, add 2 to it, and assign it back into n. So we're increasing n by 2 each time we run the loop. The question is, how many 2's do we add to n? How many times do we run the loop? How many times does this loop run? That's how many times we add 2 to n. If the loop ran 100 times, we would add 200 2's to n. We'd add 200, right? So it's really n times 2 we're adding into n. So if n starts at -4 and the loop ran 100 times, we would end up with 200 minus 4, which would be 196. So n would be 196 when we finish the loop. But we don't run the loop 100 times. How many times do we run this loop? It's messy because we're starting counting at 0, which is unnatural to us. And we've got inequality here instead of, if I count to 3, I hit the 3. I'm not counting to less than 3. So there's that awkwardness there. So you have to get used to thinking about this. Think about it this way. I starts at 0. Then it goes to 1. So it starts at 0 and does the loop. It goes to 1 and it does the loop. It goes to 2 and it does the loop. What's the highest value that I hits where it still does the loop? 2, 2, 1. Because 2, 2, 1 is less than, strictly less than 2, 2, 2. Then it does the loop. As soon as I hits 2, 2, 2, it's no longer strictly less than 2, 2, 2. So I hits 2, 2, 1. So if you were to count to 2, 2, 1, you would start at 1 and you would get to 2, 2, 1. Right? But we're starting at 0. So I takes on the values 0 through 221. How many different values does it take on?
222.
222 values. If it started at 1 and we took on the value of 221, that would be 221 times. But we started at 0. So I took on 222 different values that made the loop condition true. So what's the answer?
442.
Good. You know what? I don't want to hit this yet because I got to check my answer, right? So I don't want to look. Let me reason through it here. So the loop runs 222 times. We went through that already. So that means we're adding 222 twos. That's 444, right? But n starts at -4. And we add 444 to it. So that gives us 440. And that's your answer, right? Would you bet $10?
I would.
There's a risk here. I mean, we're in a quiz, right? We got to put an answer down. We could sit there and think about it harder, invest time and energy into it, or we can move on. What is it worth? What is the right answer worth to you? And if I get the wrong answer now, I feel embarrassed, right? Well, I'm the professor. I'm supposed to be able to figure this out, and I got it wrong. So there's something at stake, right? So in the quiz, there's there's something that's at stake for you, and you need to go through this is why you need to practice analyzing code on your own. Don't type it in there and run it and compile and run it. Think it through. Use your reasoning. Develop your skill at reasoning about algorithms. And practice for the quiz. So you're confident with your answer. Well, how do we know? I'm the one who put that in there, right? So maybe I'm wrong. To really know, we'd have to type it up and test the program, right? So you can do that. After you go through the exercises and you figure out what your answer is, and you make a strong mental effort to do that, then code it up, run it, and verify that what you came up with was correct. That would be a great exercise to do. All right. Someone some time ago asked about the post-increment and pre-increment and what the difference was. So the purpose of this problem is to make sure that you understand the difference between pre and post-increment. Here it is. When the increment operator follows the variable that it operates on, it's called a post-increment. When the increment operator precedes the variable it operates on, it's called a pre-increment operator, pre-increment. And both of these expressions that I have highlighted increment the variable by 1. Right? They increment, increment by 1, but you increment, right? You add 1 to the variable. Can you increment by 2? Is that correct English statement? Increment by 2. It's meaningful to us, so we can say it that way. So when we increment n and we increment k, so what's the difference here? So the post-increment means we do the increment after the enclosing statement is evaluated. And the pre-increment means we do the increment before the enclosing statement is evaluated. So the pre-increment is the easiest to understand. Let's look at this. We start by declaring n, setting it to 9. And then we assign something to k. What is it that we assign to k? Well, we assign the result of that expression. Now, the assignment operator has very low precedence. So that's the thing we do last, even though it's the leftmost operator in the statement. It's the last operator that's evaluated. These other operators are evaluated before assignment. But which operator is done next? It is not multiplication, because just like math, we're using parentheses to tell the compiler that we want to evaluate this expression first before multiplying by 2. So it's just like math. So the last thing we do is assignment. Before the last, we do multiplication. So what is it that we do here? We have two operators. We have post increment, and then we have the addition. Which operator goes first? Well, post means after. So we always delay that to the very end. So we add 1 to n. And n is 9. So when we add 1 to n, the expression that I have highlighted right there evaluates to 10. And that 10 is used to multiply by 2 to give us 20. And the 20 is assigned into k. And now we increment n. Got it? So k becomes 20. Then after k becomes 20, n becomes 10. All right, so wait a minute, I'm going to forget stuff. So we figured out that k became 20 and n became 10 after the second statement finishes. I wrote that down so I wouldn't forget it.
What's in the parentheses is what n becomes.
What's that?
What's in the parentheses is what n becomes.
No. N becomes whatever it was before plus 1. What's inside the parentheses has nothing to do with what n becomes.
If you were to see out statement, it would display as 10.
Huh?
If
Oh,
were to
are you
see
talking about the third statement? Or the second? We're talking about the second statement or third statement?
That's all.
So if you were to see out statement, it would display as 10.
Huh?
A see out statement for n, it would display as 10 then?
Yeah. Let's do it. I'm going to do it. All right, so there's doubt here. Let's, I'm going to go, there is reasonable doubt. Let's do this.
Yeah. So 10 plus 20.
What does this print? Now remember, there's $10 on the table. You got to get this, or you lose the $10. What does it print? And you fail the quiz. And you don't get the job. No. Oh, no. What does that print? Everybody should have an idea. What does that print? Based on what I explained. I'm going to hit enter. Money's on the table. Everyone who wants to bet for 9 goes here, $10. Everyone who wants to bet for 10 goes out. Is it 9 or 10? 10? 9? How many people want to know what I think? See how much you respect me. I think, and I'm a little nervous here to tell you the truth, but I'm going to say, what should I say, Ryan?
You should say
9, okay. Got it? Ryan gets the pot. Everybody hand over your $10. All right, so we got that, hopefully. Now this is easier to remember, easier to evaluate. We're going to do this last. we see a pre-increment in there. It's like the pre-increment has absolutely the highest priority. So we'll just do that first. No question. And a post-increment has got the worst priority, or the worst precedence. So it's absolutely going to do that last. So we're going to increment K here. So I'm going to make a mental note here. And K is 21 now. After K becomes 21, we will add its value, 21, to whatever N is. Oh, I don't remember what N is, but I do remember making a note of what it is. So it is, in fact, 10. So we're going to add to 10 plus 21. That gives us 31. So this whole thing evaluates to 31. And then we use the modulo operator. What is modulo operator? It means take the left-hand side, divide by the right-hand side, and throw away the quotient and keep the remainder. So it's give me the remainder after division. So if we take 31 and we divide by 3, what remainder do we get? We get 1. So this modulo operator with these two operands, left and right-hand side, that this evaluates to 1. So we print 1. Our answer is 1. And this is what it looks like when you submit your work. Just like that. Maybe I want to clean this up a little. That's what my answers are going to look like. Okay. Any questions on that one? Sorry. Where are we? Right there. All right, let's move to the next one. Do we have time? No, I think we're out, right? We're finished. Any questions? Concerns? So I'll be in lab. I'll see those who are